Hello everyone, today we're doing chapter 11, problem 26, and this problem gives us two structures of two different drugs. One is a lung cancer treatment drug that was introduced in 2004, and one is an inhibitor for bacterial fatty acid synthesis. So let's start with A regarding these questions. So A is regarding our lung cancer drug. So it asks, which carbon-hydrogen bond is most acidic? So carbon-hydrogen bond in terms of acidity, so obviously it's not going to be your nitrogen hydrogen bond. It's going to be some sort of carbon-hydrogen bond. So all of these have carbon-hydrogen, carbon-hydrogen, carbon-hydrogen. So your most acidic CH bond is going to be the bond in which its conjugate base, so when it gets deprotonated to make a carbanion, it's the one with when its conjugate base is going to have the highest pKa. So the highest pKa is going to be the most acidic. Why is that? Well, because what does acidic mean? It means that something is willing to give up its proton. So you can think of, is this more willing to give its proton or this? Well, we know that the conjugate base of a carbanion on a triple bond alkyne is stabilized due to its S characteristics, SP characteristics. So we know that because of the 50% S characteristics, this is going to be, the conjugate base is going to be stabilized more so than this sp2 carbon here. So because of that, we know that this is 50% S characteristic, this is 33% S characteristic. So the larger characteristic of S orbital, the more stabilization the conjugate base is going to have, meaning the higher the pKa, meaning the most acidic. So that means that this is your most acidic proton carbon bond. Now, the next question also refers to this and asks, what orbitals are used to form the shortest CC single bond in the drug? So remember, we have sp orbitals in this molecule. So an s orbital, so if we have just a straight chain, your s orbital will directly overlap. So directly overlap both of them, while your p orbitals are weaker because they're out on the side. So obviously your S directly overlaps with electrons in the middle, so it's going to be very strong and very short. So whatever bonds have highest degree of S orbital properties is going to be your shortest, strongest bond. So if I pick, for example, let's choose these bonds here, well, we need to actually read the question more carefully because it says the shortest carbon-carbon single bond. So this is a carbon-carbon triple bond. So even so, I'll show you guys, this would be sp, sp, and we know it's going to be sp. Why? Because on this alkyne, so let me draw it down here, on this alkyne, we're interested in this carbon. Well, it has two substituents, one being this group over here, one being the group down here. So this we know is an sp carbon. Why? Because s is to the power 1, p is to the power 1. So 1 plus 1 equals 2 of these substituents, which it has. And then we have both of those. So on the other side, one of the substituents is this hydrogen atom, and the other substituent is this whole group. So once again, we know as two substituents, so s to the power 1, p to the power 1, 1 plus 1 equals 2 different things bound to it. So now let's look at the carbon right next to it. So this is a single bond. So this is actually what the question is addressing. And here, so let's draw that down here. So we have, so we're interested in this single bond. So we're interested at the carbons that make the single bond. So it's this carbon and this carbon. Well, the bottom carbon, following your octet rule, we know has a proton. So we have 1, 2, 3 substituents on this carbon. So this is sp2. Why? Because s is to the power 1 and p is to the power 2. So 2 plus 1 equals 3 of these substituents. And it's attached to a carbon that has 1, 2 substituents. So that's sp. Well, this bond right here, this single carbon bond, has 33 S characteristics on the lower carbon and 50% S characteristics on the upper carbon. So now the other type of bond we have is this straight chain carbon here. So we know that each side has 2 protons. So now let's figure out what type of orbital that would have. So we're interested in these two carbons that make up this bond. So we're interested in this carbon and this carbon. And we know that this carbon is bound to one substituent, 2, 3, and then this 4. So this has 4. So it's going to be sp3. Why? Because s is to the power 1. 1 plus 3 equals 4 of these substituents. And this carbon is the same. So it's sp3, sp3. So this is 25% s on both sides. So the only other type of single bonded carbon we have is something like this. So as we determined before, this has 3 substituents. So these are sp2 carbons each. So that means it's 33% s characteristics, both of them. So remember, the shortest, strongest bond is going to be the bond that has the highest s characteristics. So now let's look at what we have. We have 3 unique type of carbons. We have this single bond carbon here, we have this single bond carbon here, and we have this type of single bond carbon here. And obviously there's more examples of them, but they're all the same type of carbon, the carbon-carbon single bond. So if you look at this, obviously this one has 25% S characteristic. This one has 33% each, so this is higher than this. That means this is going to be a shorter bond than this, but this one has 33% on one side and 50% on the other side. So this is going to have the highest proportion of S characteristic. So this bond right here is going to be your shortest bond because of that highest percentage of S characteristic. Next, see which hydrogen atom in this inhibitor is most acidic. So your most acidic means that its conjugate base is most stabilized, and one way we can stabilize a conjugate base is by resonance. So if we try to, for example, remove this proton here, you get a carbanion, and there's nothing really stabilizing that carbanion, but we all know that carboxylic acids in nature have a pKa of very close to 2 or 3, so in nature that they're going to be deprotonated. Why? Because the conjugate base, so let's say this gets deprotonated, so the conjugate base is resonance stabilized. So that means that that extra lone pair electron that's on the oxygen nucleus can actually form a new double bond here, kicking this up. So you would get some sort of resonance structure that looks like this. And remember, resonance structures decrease the energy of your intermediates or your conjugate bases, so it increases the stability. So in essence, this actually molecule exists in some sort of state where it's fluctuating these pi bonds between these two sites. So we actually don't know exactly where it is, so it's kind of a constant state of fluctuation. So we just draw dotted lines representing the pi bond could be at any of these two locations. So obviously because of the stabilization, we know that this is going to be the most acidic proton. The last question asks us to rank the labeled bonds, so 1, 2, and 3, in this acid in order of increasing bond strength. So if you remember from the previous example, increasing bond strength is due to higher percentage of S characteristics. So the higher S characteristic you have, the shorter your bond is going to be, meaning that the stronger it's going to be and the more energy it's going to require to break it. So let's look at 1. So 1 is composed of this carbon and this carbon, these two carbons. So let's draw that out. So we have this carbon has 2 protons. This carbon has no protons because it has already have 4 bonds. Remember, you have to satisfy your octet rule, so carbon makes 4 bonds. So we see at this carbon we have 1 substituent, 2, 3, and 4. So this is going to be an sp3 carbon. Remember, s to the power 1, 1 plus 3 equals 4 substituents, and it's bound to a, well, this carbon has 1 substituent, 2 substituents, so this is an sp carbon. So this carbon number 1 single bond has a 25% S characteristic on one side and a 50% S characteristic on the other side. So now 2, we have 2 equivalent carbons, so they both have the same substituents attached to it, which is 1 substituent, 2 substituent. So these are going to be both sp carbons. So on both sides, there's going to be 50% S characteristic. 3, well, on this lower side, we have 4 substituents, so that's going to be an sp3 carbon, and that's attached to the upper side, which has 1, 2, 3 different substituents, so that's going to be an sp2 carbon. So we know that this is going to be 25% S with 33% S. So remember, the highest percentage of S characteristic is going to be your strongest, shortest bond, and because it's the strongest, it's going to have the highest energy or highest strength for its dissociation. So obviously, number 2 with 50% on both sides, S characteristic, is your strongest bond. The next strongest, well, let's see what we have. We have a 25 and 50%, and we have a 25 and 33%. So obviously, 25 and 50% is greater than 25 and 33. That leaves us with bond 3.